Today we're diving into a paper that explores a fascinating area of large language model, LLM development, self-correction. The paper, Training Language Models to Self-Correct via Reinforcement Learning, proposes a novel approach called SCORE to enhance LLM's ability to identify and fix their own mistakes. What are the key challenges in training LLMs to self-correct?
The main challenge lies in the fact that LLMs often lack the ability to reliably assess their own responses. They might contain the necessary knowledge to arrive at the correct answer, but struggle to effectively utilize it when needed. This is particularly evident in tasks requiring reasoning, such as mathematical problem solving or code generation. Existing approaches for training self-correction either rely on multiple models or require external supervision, which limits their practicality.
So SCORE aims to address these limitations by using reinforcement learning, RL. Can you elaborate on how SCORE works?
SCORE employs a multi-turn online RL approach, meaning it trains the LLM to generate multiple attempts at solving a problem, with each attempt building upon the previous one. The model learns to self-correct by optimizing its responses based on the reward it receives for each attempt. This is done entirely through self-generated data, eliminating the need for external supervision.
That's interesting. But how does SCORE overcome the challenge of distribution mismatch between training and inference?
SCORE addresses this by training the model on its own distribution of self-generated correction traces. This ensures that the model learns to correct its own mistakes effectively, rather than simply fitting to a specific data set of predefined errors.
You mentioned that SCORE operates in two stages. Can you explain the purpose of each stage?
The first stage focuses on training a model initialization that is less prone to collapse during subsequent RL training. This is achieved by explicitly teaching the model to correct its second attempt responses while constraining the first attempt to be similar to the base model's output. This helps prevent the model from simply learning to produce the best possible first attempt and then making only minor edits in the second attempt.
And what about the second stage?
The second stage involves running multi-turn RL to optimize the reward for both attempts. However, it incorporates a reward bonus term that encourages the model to improve its responses from the first attempt to the second. This further biases the learning process towards a self-correcting strategy.
So SCORE essentially guides the model towards learning a self-correction strategy by shaping the reward function. Can you elaborate on how this reward shaping works?
The reward shaping mechanism assigns a higher reward to traces where the model successfully corrects its initial mistake. This incentivizes the model to learn a strategy that actively seeks to improve its responses, rather than simply relying on its initial attempt.
That makes sense. Can you provide some examples of how SCORE performs in practice?
The paper evaluates SCORE on two tasks: mathematical problem solving on the math dataset and code generation on the HumanEval benchmark. The results show that SCORE significantly outperforms baseline methods, achieving a positive self-correction rate and improving the model's accuracy at both the first and second attempts.
That's impressive. Can you elaborate on the specific improvements SCORE achieves on these tasks?
On the math dataset, SCORE achieves a 15.6% improvement in self-correction performance compared to the base model. It also demonstrates a significant increase in the number of problems that are correctly solved after the second attempt. On HumanEval, SCORE achieves a 9.1% improvement in self-correction performance, indicating its effectiveness in improving code generation accuracy.
These results are quite promising. What are the key takeaways from the paper's ablation studies?
The ablation studies highlight the importance of each component of SCORE. They show that multi-turn training, the two-stage structure, and reward shaping are all crucial for achieving positive self-correction performance. The studies also demonstrate that using on-policy RL, where the model learns from its own generated data, is essential for effective self-correction.
So SCORE is a significant step forward in training LLMs to self-correct. What are some of the limitations of this approach?
One limitation is that SCORE is currently evaluated for only one round of self-correction. Further research is needed to explore its effectiveness for multiple rounds of iterative self-correction. Additionally, the two-stage structure of SCORE could be further optimized by unifying the two stages into a single training process.
What are the broader implications of this research?
This research suggests that learning complex meta-strategies, such as self-correction, might require going beyond traditional supervised fine-tuning and single-turn RL. Multi-turn RL, as demonstrated by SCORE, offers a promising approach for training LLMs to implement nuanced strategies. Furthermore, the success of SCORE highlights the potential of using more detailed supervision and reward shaping to guide LLMs towards learning effective and generalizable behaviors.
So, SCORE is a valuable contribution to the field of LLM development, offering a novel and effective approach to training self-correction capabilities. What are some potential future directions for this research?
Future research could focus on extending SCORE to handle multiple rounds of self-correction, unifying the two stages into a single training process, and exploring the use of more detailed supervision and reward shaping to further enhance the model's self-correction abilities. Additionally, investigating the application of SCORE to other tasks, such as question answering and text summarization, could be a fruitful area of exploration.
Thank you for sharing your insights on this fascinating research. It's clear that SCORE holds significant potential for advancing the capabilities of LLMs and enabling them to learn more complex and nuanced behaviors.